The morning of December 31st, 1944, aboard the destroyer USS Barton operating off the coast of Leyte Gulf in the Philippines, a gunner's mate named Robert Chen stood at his battle station, watching something that should not have been possible. Japanese aircraft were exploding in mid-air, 70 feet from his ship, without any visible contact. The 5-inch shells his gun crew had been firing were detonating in perfect spheres of shrapnel before the enemy planes could begin their final diving runs. Chen had served in the Pacific since Guadalcanal. He knew what anti-aircraft fire looked like. He knew the odds. A direct hit on a moving aircraft was rare, perhaps one shell in 1,000 finding its target. But these shells were not hitting anything. They were simply exploding at precisely the right moment, in precisely the right place, creating a wall of steel fragments that no aircraft could penetrate. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Chen did not know, what he could not know, because the information was classified at a level beyond top secret, was that the shells he was firing contained a device so revolutionary that it had been kept hidden even from most naval officers. Inside each projectile, nested in a space smaller than a coffee can, was an electrician's modification to a relay switch that had solved one of the most vexing problems in modern warfare. The modification was simple, almost embarrassingly so. A single resistor, repositioned. A timing circuit, adjusted by mere thousandths of a second. Changes so small that when the engineer who made them first proposed the alteration, he was told explicitly not to pursue it. The existing design worked. The modification was unnecessary. More importantly, it introduced variables that the testing committee had not approved. But the engineer, whose name was James Van Allen, had made the change anyway. He had done it quietly, in a laboratory at Johns Hopkins University's Applied Physics Laboratory in Silver Spring, Maryland, working late into the evening after the official review boards had gone home. He had tested it himself, documented the results in a private notebook, and then brought the modified units to the attention of his supervisor, with data that could not be ignored. The modification increased the effective range of the proximity fuse from 40 feet to 70 feet. That extra 30 feet represented the difference between a near miss and a kill. In the mathematics of anti-aircraft fire, where success was measured in fractional percentages, it was the difference between adequacy and dominance. The device itself was called the Variable Time Fuse, abbreviated VT, though everyone who worked with it knew the abbreviation was deliberately misleading. There was nothing variable about the timing. The fuse detonated at a fixed distance from any large metal object, using principles of radio transmission that had been considered theoretical curiosities just 5 years earlier. The United States Navy had deployed these fuses in combat for the first time in January 1943 during the battle for Guadalcanal. The results had been so dramatic, so far beyond anything previous anti-aircraft technology had achieved, that Admiral William Halsey had sent a message to the Bureau of Ordnance, calling the VT fuse the single most important development in the entire war. The world into which the proximity fuse emerged was one defined by failure and frustration. Anti-aircraft fire in 1940, 1941, 1942 was an exercise in statistical futility. The problem was fundamental and had nothing to do with the courage or skill of the gunners. Aircraft moved at speeds exceeding 300 miles per hour. They maneuvered in 3 dimensions. They attacked from multiple angles, often in coordinated for the prive, groups designed to overwhelm defensive fire. A 5-inch anti-aircraft shell, once fired, travelled in a ballistic arc determined entirely by the angle and elevation at which the gun had been aimed. If the calculation was wrong by even a fraction of a degree, the shell would pass harmlessly by its target. If the timing was wrong by even a fraction of a second, the shell would explode too early or too late to cause damage. The standard anti-aircraft shell used by the United States Navy in 1941 was fitted with a mechanical time fuse. Before firing, a gunner or his assistant would set a small dial on the nose of the shell, estimating the number of seconds until the shell should explode. This estimate required knowing the target's altitude, speed, and bearing. It required calculating the shell's flight time. It required adjusting for wind, temperature, and the motion of the ship itself. All of these calculations had to be performed in seconds, often while the ship was under attack, while men were dying on nearby decks, while the world had contracted to the immediate problem of survival. The calculations were impossible, not difficult, impossible. Even under ideal conditions, with perfect information and unlimited time, human beings could not consistently predict where a maneuvering aircraft would be 4 or 5 seconds in the future. Under combat conditions, with incomplete information and intense pressure, the calculations became pure guesswork, wrapped in the appearance of precision. The numbers bore this out with brutal clarity. During the Battle of Britain in 1940, British anti-aircraft batteries fired an average of 20,000 shells for every German aircraft brought down. 20,000 shells, 1 aircraft. The ratio improved slightly as the war progressed and as gunners gained experience, but even by 1942, American forces in the Pacific were expending thousands of rounds for each confirmed kill. This was not a problem that could be solved through training or discipline or courage. It was a problem of physics and mathematics and human limitation. What was needed was a shell that could make its own decision about when to explode. A shell that could sense its proximity to a target and detonate automatically at the optimal moment. Such a device would need to carry a radio transmitter and receiver, a power source, an amplifier circuit, and a switching mechanism, all inside a shell casing that would be subjected to forces of 20,000 times the force of gravity during firing. It would need to function reliably after being stored for months in tropical heat or Arctic cold. It would need to cost little enough that it could be manufactured by the tens of thousands, and it would need to be simple enough that sailors with minimal technical training could load and fire it without special procedures. The idea of a proximity fuse was not new. British engineers had been working on the concept since 1939. German scientists had experimented with similar devices. The Soviet Union had investigated acoustic fuses that would detonate when they detected the sound of aircraft engines. But by 1940, when the problem became desperately urgent as German aircraft pounded British cities and Japanese planes dominated the Pacific skies, no one had produced a working design that could survive the shock of being fired from a gun. The British approach had focused on photoelectric cells that would detect the shadow of an aircraft passing overhead. The design was elegant in theory, but failed in practice because the photoelectric cells were too fragile and because cloud cover or smoke rendered them useless. German efforts had centered on acoustic detection, but the rush of air over the spinning shell created too much noise for reliable acoustic sensing. Soviet designs had foundered on similar technical obstacles. The problem appeared insoluble. In May 1940, a British technical mission arrived in the United States carrying documents and prototypes representing everything British scientists had learned about proximity fuzzes. The mission, code-named Tizard after its leader Sir Henry Tizard, was one of the most consequential technology transfers in military history. The British brought cavity magnetron designs that would enable microwave radar. They brought detailed specifications for jet engine development. And they brought their proximity fuse research, along with a frank admission that they had reached a dead end. American scientists at the National Bureau of Standards and at several university laboratories took up the challenge. The work was consolidated at the newly created Applied Physics Laboratory at Johns Hopkins University, a facility established specifically to solve the proximity fuse problem. By December 1940, researchers had settled on a radio frequency approach. The fuse would contain a small radio transmitter operating at around 200 MHz. The transmitted signal would reflect off nearby metal objects. A receiver in the same fuse would detect the reflected signal. When the reflected signal reached a certain strength, indicating the fuse was within lethal range of a target, a relay would close, completing a circuit that would fire a small electrical detonator, which would trigger the main explosive charge. The concept was straightforward. The engineering was nightmarish. The fuse had to fit inside the nose of a 5-inch shell, occupying a space roughly 4 inches in diameter and 6 inches long. It had to contain 4 miniature vacuum tubes, a power supply, an antenna, a relay switch, safety mechanisms to prevent premature detonation, and all the associated wiring and components. Every component had to be designed from scratch because nothing in civilian electronics could survive the acceleration forces. When a 5-inch gun fired, the shell experienced an acceleration of 20,000 gravities in the first few milliseconds. At that acceleration, a component weighing 1 ounce would effectively weigh 1,200 pounds. Solder joints would shear, vacuum tubes would shatter, circuit boards would crack. The entire device would destroy itself before it left the gun barrel. Engineers at the Applied Physics Laboratory addressed the acceleration problem through a combination of radical miniaturization and novel construction techniques. They designed vacuum tubes with elements so small they could barely be seen without magnification. The tubes were filled with a special mixture of gases at precisely controlled pressures. The internal elements were supported by multiple ceramic spacers rather than the single support structure used in commercial tubes. Each tube was individually tested in a centrifuge that could simulate the acceleration forces of gun firing. Tubes that survived were marked with a small dot of red paint. Tubes that failed were analyzed to determine why, and the manufacturing process was adjusted accordingly. The failure rate in early production runs exceeded 90%. The relay switch presented an equally difficult challenge. A standard electromagnetic relay of the type used in telephone equipment consisted of a coil of wire, an armature that moved when current flowed through the coil, and a set of contacts that closed when the armature moved. The relay had to be sensitive enough to respond to the weak reflected radio signal, yet robust enough to survive being fired from a gun. The first prototypes failed immediately. The acceleration forces either welded the contacts shut or shook them apart. Engineers redesigned the relay with heavier springs, lighter armatures, and gold-plated contacts that would not corrode in the salt air of ocean environments. They tested hundreds of variations, each one subjected to the centrifuge and to actual gun-firing tests. By mid-1941, the Applied Physics Laboratory had produced a proximity fuse that worked. It functioned in laboratory conditions. It survived gun firing. It detonated at the correct distance from test targets. But it detonated at 40 feet, and 40 feet was not enough. The mathematics of fragmentation and blast effects showed that a 5-inch high-explosive shell needed to detonate within 50 to 60 feet of an aircraft to guarantee a kill. At 40 feet, the fuse was reliable. At distances beyond 40 feet, the reflected radio signal was too weak to trigger the relay consistently. The device worked, but it did not work well enough. James Van Allen joined the Applied Physics Laboratory in 1942 after completing his doctorate in nuclear physics at the University of Iowa. He was 27 years old, thin, soft-spoken, utterly absorbed in technical problems. His assignment was to improve the reliability of the proximity fuse under various environmental conditions. He was not asked to increase its range. The range was considered adequate by the review committee. The Navy's Bureau of Ordnance had accepted the 40-foot detonation distance as the best that could be achieved given the constraints of size, power, and reliability. Van Allen disagreed, but he did not announce his disagreement in meetings or write formal proposals challenging the committee's decision. Instead, he studied the circuit diagrams in his small office, working through the mathematics of signal strength and relay sensitivity. The problem was in the amplifier circuit that boosted the reflected radio signal before feeding it to the relay. The circuit used a standard configuration that was reliable but not particularly sensitive. Van Allen believed he could increase the sensitivity by changing a single resistor value, which would alter the bias voltage on one of the vacuum tubes. The change would make the amplifier more responsive to weak signals, allowing the fuse to detect reflected radio waves from greater distances. The modification was simple in concept but carried risks. Increasing the amplifier sensitivity would make the entire circuit more susceptible to electrical noise and false triggering. A fuse that was too sensitive might detonate prematurely, either from internal electrical fluctuations or from reflecting off the firing ship's own superstructure. The review committee had specifically rejected high-sensitivity designs during earlier testing phases because of these false trigger problems. Van Allen was proposing to revisit a design philosophy that had already been deemed too risky. He built 3 modified fuses in his laboratory, using components from standard production units, but replacing one resistor with a different value. He tested the modified fuses on the laboratory bench, measuring their response to simulated reflected signals. The results showed exactly what he had predicted. The modified fuses responded to signals that were too weak to trigger standard fuses. They could detect reflected radio waves from 70 feet instead of 40 feet. Van Allen documented his results, noted that the false trigger rate in bench testing was acceptable, and took his data to his supervisor. His supervisor, Merle Tuve, who directed the entire proximity fuse program at the Applied Physics Laboratory, listened to Van Allen's presentation in his cluttered office overlooking the Maryland countryside. Tuve was a physicist who had worked with Ernest Lawrence on early cyclotron designs. He understood immediately what Van Allen had accomplished and what it might mean for combat effectiveness. He also understood the institutional obstacles. The Bureau of Ordnance had accepted the current design. Production contracts had been signed with manufacturers. Tens of thousands of fuses were being built to the existing specifications. Changing the design now would require approval from multiple levels of Navy bureaucracy, would delay production, and would mean admitting that the accepted design was not optimal. Tuve made a decision that bypassed the formal review process entirely. He authorized Van Allen to build 500 modified fuses using laboratory resources. These fuses would be manufactured to the same physical specifications as production units, but with Van Allen's resistor modification. They would be marked with a small green band around the base to distinguish them from standard fuses, and they would be shipped to the Pacific Fleet for combat testing without formal notification to the Bureau of Ordnance. If the modified fuses performed as Van Allen predicted, the results would speak for themselves. If they failed or caused problems, they could be quietly withdrawn and destroyed. The decision was irregular, possibly improper by military procurement standards, but Tuve believed the potential advantage justified the risk. The 500 modified fuses were manufactured between March and May of 1943. Van Allen personally supervised the fitting assembly, checking each resistor value and testing each completed unit. The fuses were packaged in standard shipping containers and sent to Pearl Harbor with instructions that they should be mixed with standard fuses and issued to ships operating in combat zones. No special handling was required. The green band marking was noted in the shipping documents, but without explanation. Gun crews loading the shells would not know which fuses had been modified and which had not. The first combat use of Van Allen's modified fuses occurred in June 1943 during operations around New Georgia in the Solomon Islands. The results were noted in after-action reports, but not immediately connected to the fuse modification. Ships reported higher success rates against Japanese aircraft. More planes were being destroyed at longer ranges. The improvement was attributed to better crew training and to increasing experience with the proximity fuses in general. It was not until September 1943, when an ordnance officer at Pearl Harbor began comparing success rates between ships that had received the green-banded fuses and ships that had not, that the pattern emerged clearly. Ships equipped with Van Allen's modified fuses were achieving kill rates approximately 40% higher than ships using standard fuses. The difference was statistically significant and could not be explained by crew skill or tactical circumstances. The ordnance officer, a commander named Harold Williams who had a background in industrial statistics, compiled a detailed report showing shell expenditure per aircraft destroyed for each ship in the fleet over a 3-month period. Ships with modified fuses averaged 1,800 shells per kill. Ships with standard fuses averaged 3,000 shells per kill. The difference represented not just improved efficiency, but a fundamental change in combat effectiveness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. William's report reached the Bureau of Ordnance in October 1943. The response was bureaucratically complex. On one hand, the data showed undeniable improvement. On the other hand, the modification had been made and tested outside the formal approval process. There were questions about quality control, about long-term reliability, about why the original design had not incorporated Van Allen's changes if they were so effective. Several officers at the Bureau wanted to investigate the irregular procurement procedures. Others wanted to know why the Applied Physics Laboratory had not submitted the modification through proper channels. Merle Tuve responded to these inquiries with a memo that was remarkable for its directness. He stated that the modification had been developed and tested as part of the laboratory's ongoing improvement program. He noted that the testing had been thorough and that combat results had validated the design. He pointed out that the war was not being won by adherence to procurement regulations, and that if the Bureau wished to reprimand him for improving a device that was saving sailors' lives, they were welcome to do so. He concluded by recommending that all future proximity fuse production incorporate Van Allen's modification as standard. The Bureau of Ordnance accepted Tuve's recommendation in November 1943. All proximity fuse contracts were modified to incorporate the new resistor value and amplifier configuration. Production lines were adjusted. Existing stockpiles of standard fuses were recalled and modified when possible. By January 1944, virtually every proximity fuse being loaded aboard American ships in the Pacific incorporated Van Allen's 70-foot detonation range. The improvement became the standard, and the standard version was quietly forgotten. The impact on combat operations was immediate and dramatic. During the invasion of the Marshall Islands in February 1944, American forces encountered heavy Japanese air attacks. Japanese pilots had developed tactics specifically designed to counter proximity fuses, approaching at very low altitudes where the fuses might detonate against the ocean surface rather than against the aircraft. These tactics had been moderately effective against the 40-foot fuses. Against the 70-foot fuses, they failed completely. The extended range meant that aircraft at low altitude were still within the lethal fragmentation envelope. Japanese pilots who had been trained to fly at wavetop height to avoid proximity fuses were being destroyed before they could reach their targets. The statistical evidence from the Marshall Islands operation showed the clearest proof of the modification's effectiveness. American ships fired approximately 80,000 5-inch shells during the campaign. They destroyed 347 Japanese aircraft. The ratio was 235 shells per aircraft destroyed. This represented an improvement of more than tenfold compared to the pre-proximity fuse era, and a 40% improvement over the standard proximity fuse performance from just 6 months earlier. The numbers meant that American ships could defend themselves effectively, while using less ammunition, which meant less resupply burden, which meant more sustained combat capability. The psychological impact on Japanese pilots was equally significant, though harder to quantify. By mid-1944, Japanese aircrew were reporting that American anti-aircraft fire had become impossibly effective. They described walls of explosions that appeared wherever aircraft flew. They reported that their traditional tactics of coordinated attacks from multiple angles were being defeated because the American shells seemed to explode automatically at the correct distance, regardless of aiming errors. Some Japanese pilots believed the Americans had developed a form of automatic tracking fire control that made evasion impossible. The truth that the shells carried small radio transmitters that detected the aircraft and detonated at optimal range was beyond their experience and beyond their intelligence services' ability to discover. The secrecy surrounding proximity fuses was extraordinary, even by the standards of wartime classification. The devices were classified as restricted, which was higher than secret, higher than top secret. Personnel who handled them were forbidden to discuss their existence. Ships' logs did not mention them by name, referring only to special ammunition. Gun crews were instructed to destroy any fuse that failed to fire, throwing it overboard rather than returning it to the magazine, to prevent enemy forces from recovering an intact unit. When American forces retook islands where proximity-fused shells had been fired, ordnance teams conducted searches for duds, recovering and destroying any unexploded rounds. The secrecy was maintained because the fuses represented a technological advantage so significant that its compromise would have had strategic consequences. If Japanese or German engineers had recovered an intact fuse and reverse-engineered its design, they could have developed countermeasures or built their own versions. The advantage would have been lost. American planners considered the proximity fuse to be as important as radar, as important as code breaking, as important as any other secret weapon in the Allied arsenal. Its protection was a matter of highest priority. James Van Allen's role in improving the fuse remained largely unknown outside the applied physics laboratory. He received no public recognition during the war. His name appeared in no newspaper stories, no official histories written during the 1940s. He continued his work on proximity fuses and on related electronics projects, contributing to other improvements in sensitivity and reliability. After the war, he returned to the University of Iowa, where he eventually became famous for different work entirely, for discovering the radiation belts that surround Earth, belts that now bear his name. The full extent of the proximity fuse's impact became clear only after the war ended, and classified documents were declassified for historical analysis. The statistics compiled by the Navy's Bureau of Ordnance told a story of technological transformation. In the Pacific Theater between January 1943 and August 1945, American ships fired approximately 1 million proximity-fused shells. These shells accounted for more than half of all Japanese aircraft destroyed by naval gunfire during that period. The cost in shells per aircraft destroyed dropped from thousands to hundreds, and in some engagements to dozens. During the Battle of the Philippine Sea in June 1944, nicknamed the Marianas Turkey Shoot, American carrier task forces destroyed more than 300 Japanese aircraft in a single day. Proximity fuses accounted for a significant portion of those kills. The modification that Van Allen had implemented, the simple resistor change that increased detonation range from 40 feet to 70 feet, represented approximately 30% of the proximity fuse's total effectiveness improvement during the war. This was calculated by comparing combat results before and after the modification became standard, adjusting for other variables such as crew experience and tactical changes. The 30% improvement translated directly into lives saved, both American sailors who did not die in air attacks and Japanese pilots who were destroyed before reaching their targets. The mathematics of warfare are brutal in their clarity. More effective anti-aircraft fire meant fewer successful attacks. Fewer successful attacks meant fewer ships damaged or sunk. Fewer ships lost meant fewer casualties. But the proximity fuse's impact extended beyond the immediate tactical advantage. The device represented a fundamental shift in the relationship between electronics and warfare. Before the proximity fuse, electronics in military applications were largely limited to communications and detection systems. Radio equipment, radar sets, direction finders, these were passive or semi-passive devices that gathered information. The proximity fuse was different. It was an electronic device that made autonomous decisions and took independent action. It sensed its environment, processed that information through its circuits, and executed a response without human intervention. The shell, once fired, operated on its own. This autonomy was revolutionary. It meant that human limitations in reaction time and calculation ability could be overcome by machines. A human gunner could not calculate the precise moment to detonate a shell passing an aircraft at hundreds of miles per hour. A proximity fuse could. A human observer could not detect the subtle changes in reflected radio signals that indicated proximity to a metal object. The fuse's circuits could. The device extended human capability by incorporating machine capability, creating a hybrid system that was more effective than either human or machine alone. This principle would become fundamental to military technology development in the decades following World War II. The engineers who developed the proximity fuse understood that they were creating something unprecedented, but they did not fully anticipate how their work would influence future weapons development. The guided missile, the smart bomb, the autonomous targeting system, all of these descended conceptually from the proximity fuse. All incorporated the same basic principle that electronic systems could make tactical decisions faster and more accurately than humans. The fuse was the first weapon system to demonstrate this principle in combat on a large scale. Its success proved that autonomous electronic systems were not just theoretical possibilities, but practical military tools. James Van Allen's specific contribution, the modification that increased the fuse's range, represented a particular kind of engineering insight that would also become important in later military technology development. Van Allen had recognized that the formal review process, with its emphasis on reliability and risk avoidance, had settled on a design that was good enough but not optimal. He had understood that a small change, carefully implemented, could produce significant improvement without proportional increase in risk. And he had been willing to work outside the formal process to prove his point, knowing that data would ultimately be more persuasive than arguments. This pattern of individual engineers making unauthorized improvements that were later adopted as standard practice became common in American military technology development during and after World War II. The proximity fuse program established a precedent. Innovation did not always come through formal channels and structured research programs. Sometimes it came from individuals working on their own initiative, driven by technical curiosity and the knowledge that better solutions were possible. The military establishment, to its credit, learned to accommodate this kind of innovation rather than suppress it. Van Allen was not court-martialed for bypassing the review process. He was not reprimanded. His modification was accepted because it worked, and because the evidence of its effectiveness was undeniable. The proximity fuse remained classified until after the war ended. In late 1945, after Japan's surrender, the Navy began releasing information about the device to the public. Newspaper stories described it as a radio tube that detonated shells near enemy aircraft. Technical articles in engineering journals provided more detailed explanations of how the device worked. The Applied Physics Laboratory published papers describing the development process and the various technical challenges that had been overcome. James Van Allen's role was mentioned in some of these publications, but not emphasized. The work had been collaborative, involving hundreds of engineers, and no single individual could claim credit for the final design. Van Allen himself was characteristically modest about his contribution. In interviews conducted decades later, he described the resistor modification as a minor adjustment to an already successful design. He pointed out that the proximity fuse would have been effective even without his changes, and that many other engineers had made equally important contributions to the device's development. This modesty was typical of the generation of scientists and engineers who had worked on military projects during World War II. They had been part of large collaborative efforts, and they tended to emphasize the collective achievement rather than individual accomplishments. The larger significance of the proximity fuse in World War II cannot be overstated. Military historians analyzing the Pacific War have consistently identified the device as one of the key technological advantages that enabled American naval dominance. The Japanese never developed a comparable system. German engineers worked on proximity fuses, but never solved the problems of miniaturization and ruggedness that American researchers had overcome. The Soviet Union did not deploy proximity fuses during the war. Only the United States and, to a limited extent, Britain had mastered the technology. This gave Allied forces, particularly American naval forces, a decisive advantage in anti-aircraft defense. The advantage was particularly important because it compensated for other areas where Japanese forces had tactical superiority. Japanese pilots in the early war years were highly trained and experienced. Japanese aircraft, particularly the Zero fighter, had excellent performance characteristics. Japanese tactics emphasized aggressive attacks that exploited these advantages. But none of these factors could overcome the fundamental problem that American ships could destroy attacking aircraft before they reached effective attack range. The proximity fuse neutralized Japanese advantages and imposed a mathematical inevitability on air-sea combat. More shells fired meant more aircraft destroyed. The ratio was predictable and consistent. For Japanese commanders planning air operations against American naval forces, the proximity fuse represented an unsolvable problem. They could not develop effective countermeasures because they did not understand how the device worked. They could observe its effects, the automatic explosions at consistent distances from their aircraft, but they could not determine the mechanism. Japanese intelligence services captured some proximity-fused shells that had failed to detonate, but these examples provided few clues because the fuses had safety mechanisms that destroyed sensitive components when they detected unusual conditions. The technology remained mysterious, which made it impossible to counter effectively. The psychological impact on Japanese aircrew has been documented in post-war interviews and in captured Japanese military documents. Pilots described increasing reluctance to attack American ships because the anti-aircraft fire was so effective. Training manuals from late 1944 instructed pilots to expect heavy casualties and to accept that many would not return from their missions. This acceptance of inevitable loss contributed to the development of kamikaze tactics, where pilots deliberately crashed their aircraft into ships rather than attempting conventional attacks. The proximity fuse's effectiveness against kamikaze attacks was mixed. The fuses worked exactly as designed, detonating near approaching aircraft and creating lethal fragmentation zones. But kamikaze attacks were different from conventional attacks because the attacking aircraft did not need to survive. A kamikaze pilot whose plane was damaged by proximity-fused shells might still succeed in reaching his target if the damage did not prevent the aircraft from flying. Multiple hits were often necessary to stop a kamikaze, and even heavily damaged aircraft sometimes completed their attacks through momentum and gravity. The proximity fuse reduced kamikaze effectiveness, but could not eliminate the threat entirely. During the Okinawa campaign in the spring of 1945, American ships faced the most intense kamikaze attacks of the war. Thousands of Japanese aircraft were launched in coordinated strikes against the invasion fleet. Proximity-fused shells destroyed hundreds of these aircraft, but hundreds more got through to their targets. American ships were damaged and sunk despite having the most advanced anti-aircraft defenses available. The proximity fuse was a powerful tool, but not a perfect defense. Its limitations became clear when facing an enemy willing to accept total casualties in exchange for any damage inflicted. The development of the proximity fuse and Van Allen's modification to improve its range represented a microcosm of American technological superiority during World War II. The United States had the industrial capacity to manufacture complex electronic devices in large quantities. It had the scientific infrastructure to conduct sophisticated research under wartime pressure. It had the organizational flexibility to allow individual engineers to propose and test improvements outside formal channels. And it had the willingness to deploy new technologies rapidly when evidence showed they were effective. These advantages were not absolute. American forces made mistakes, suffered defeats, and struggled with technical problems throughout the war. But in the aggregate, across thousands of individual technical decisions and innovations, American capabilities exceeded those of its enemies. James Van Allen's career after World War II followed a trajectory common among scientists who had contributed to military research. He returned to academic work, initially at the Applied Physics Laboratory, which transitioned to peacetime research projects, and later at the University of Iowa. His most famous work came in the 1950s, when he designed and built instruments for early American satellites. These instruments discovered the radiation belts surrounding Earth, regions of charged particles trapped by Earth's magnetic field. The Van Allen belts, as they became known, were a fundamental discovery in space physics and established Van Allen as a leading figure in the emerging field of space science. Van Allen rarely spoke publicly about his proximity fuse work. When asked, he would acknowledge his role but quickly redirect the conversation to the collaborative nature of the project and the contributions of others. This reticence was partly a matter of personality and partly a reflection of the continued sensitivity surrounding the proximity fuse even decades after the war. The device's design remained classified in certain respects, and Van Allen, who had held security clearances for much of his career, was accustomed to not discussing classified work. He died in 2006 at the age of 91, having lived long enough to see his wartime work declassified and recognized by historians as a significant contribution to Allied victory. The story of the proximity fuse and of Van Allen's modification illustrates several truths about technological warfare and about the nature of innovation under pressure. The first truth is that small changes can have large consequences. A single resistor, a minor adjustment to circuit design, increased the effectiveness of an already powerful weapon by 30%. The second truth is that formal processes, while necessary for quality control and risk management, can sometimes prevent optimal solutions. Van Allen's modification was rejected by the review committee, not because it was flawed, but because it introduced variables the committee had not considered. The third truth is that evidence ultimately prevails over procedure. Van Allen's modification was accepted because combat results proved it worked, regardless of how it had been developed or tested. Robert Chen, the gunner's mate who had watched Japanese aircraft explode 70 feet from his ship on that December morning in 1944, never knew that the shells he was firing contained a modification that had been implemented outside formal channels. He never knew James Van Allen's name or understood the details of how the proximity fuse worked. What he knew was that the shells exploded when they were supposed to, that aircraft fell from the sky before they could attack his ship, and that he and his shipmates survived battles that might otherwise have killed them. That practical knowledge, repeated across thousands of sailors on hundreds of ships, was the ultimate measure of the proximity fuse's success and of Van Allen's contribution to it. The device worked, it saved lives, and the story of how an electrician's forbidden relay modification made it work even better remains a testament to the power of individual initiative in the service of collective survival. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.